everybody. Welcome. My name is Jeffery. I'm going to be talking today about scaling teams on the Beam with Kafka. A little bit about me. I'm a staff software engineer and tech lead at theScore. Thank you. I work on our platform team. I previously worked at a different sports news and media company that's a heavy user of Elixir. You might be able to figure out who they are. There I worked on social platforms, also using Kafka pretty heavily. Got about 6 years experience in Elixir and about 4 years with Kafka. A little bit more about me. I love hunting obscure bugs in code. I'm a dad to a 3-year-old girl who also loves hunting bugs. All my formal background's in music education. I play the upright bass. I've never taken a CS class. And as such, I've managed to avoid writing any Java until about last year, and this is going to come up a little bit later in the talk. A little bit about theScore. Now, sorry, this is going to sound a little bit like a sales pitch. I don't mean it to, but the story is relevant for the rest of the talk. We're a sports news, media, and betting company. We have really strong brand recognition in Canada. We recently struck a deal with ESPN. We're going to be launching ESPN Bet in the States. Our backend's almost entirely Elixir. And we're one of the fastest growing Elixir companies. There was a study released earlier this year. I'm not sure where their numbers come from, but over the span of a year, they say we grew 250%. In 2021, we had about 8 backend teams. We also started adopting Kafka, moving away from NAT streaming in 21. I don't know if maybe you've heard of NATs. NAT streaming is a particular product built on top of that, and if you try to Google it now, you probably won't be able to find anything about it, so I think we moved away at the right time. In 2021, we also announced that we were going to launch an in-house sports book, and at the time, there was some industry criticism that, like, there's no way they can do that in a year. Well, we did. We pulled it off in a year pretty successfully. And then in 22, we also announced that we were going to be migrating Barstool, their sportsbook app, onto our platform that we built at theScore. They were a sister company of us. And there's, again, industry criticism that says, like, they're operating in 14 states in a heavily regulated industry. You're not going to be able to do that in a year. We did. We delivered. And today, we're about 25 teams. Also, we're hiring. We've got a booth in the other room if you'd like to come talk with us. Now, I say all this. It sounds like a little braggy. But my point here is we did a lot. We grew a lot, and we did a lot. We hit a lot of goals in a couple years. I'm not going to say that's because of Kafka. We've got a great team of, like, really smart people that impress me every day with how much they get done, how fast they get done, and how nice they are when they do it. If Kafka didn't exist, we would have found another way. But we've used Kafka pretty heavily to achieve some of these accomplishments. So today we're going to talk about how we've kind of done that. But first, I want to talk about my intro to Kafka, which also is my misconceptions about what it is and how it works. So about 2018, I started hearing about Kafka. I was using other messaging platforms like RabbitMQ. Started hearing about Kafka. It's really fast. It's getting a lot of traction in, like, bigger tech companies. So I went and I got a book. I love Manning books. They're great. This one's Kafka Streams in Action. The kind of subtitle here is Real-Time Apps and Microservices with the Kafka Streams API. And I thought, cool, I want real-time apps and microservices. So I get the book, I crack it open, and I start to see this. Classes, types, and semicolons. What's going on here? And then I realize, oh, this is Java. I don't do Java, especially not in 2018. I avoided it until 2022. And what I realized is this is Kafka Streams, which is a Java library. I don't think anywhere on the front or back of the book or the inside cover did it say that it was a Java book. So here I am with a Java book. And I kind of had, like, an anti-Java thing back then because I don't know if anyone here is, like, about my age, but in high school, I was, like, the coolest kid around because I had an AMD Duron 600 megahertz processor and a computer I built myself and overclocked to, like, a gigahertz. But back then, Java apps were like desktop apps that were huge memory hogs, right? If you had like OpenOffice, which was a good app, but it took, like, a lot of memory. You couldn't use other stuff when you were running Java apps. You'd always look for, like, native alternatives. So that was my opinion of Java at the time. Totally, like, off base about using Java on that server, but I thought, I don't want that. It's memory hungry. I'm not going to do it. Excuse me here. So We learned what Kafka isn't, what I thought it was and what it isn't. But what is it? What is Kafka? The tagline, like on the home page, ApacheKafka.com, whatever it is, says, it's a distributed event streaming platform. That phrase, like I understand the word distributed, kind of understand event streaming, and what does platform even mean here? When you break it down, Kafka is pretty much just a distributed and partitioned log. It's not a message bus, right? So with Kafka, you give it messages, you give it bytes, and it stores them in topics and partitions, and then you get them out in the same order on the other end. And that's almost all it does. There's some other fancy things that it does, but that's like the main way it works, and no more. You can build pub/sub patterns on top, RPC patterns, whatever you want, but that's all built on top of it. The server API is pretty simple. You define the topics that you want to interact with, and then you say there's like a poll function. It's just give me bytes from the consumer side or a publish function on the other side. But most of the smarts about what Kafka is in the clients. For example, consumer groups. If you don't know what consumer groups are, they're basically like a group of workers that are all working off the same topic. It's not like pub/sub. They don't all get the same messages. They get a portion of the messages. And that's all. The server's very little involved in that. It's mostly orchestrated through this kind of secret topic called consumer offsets. And the way it works is, let's say I'm like the sports score consumer, and I show up and I say, hey, Kafka, I'm going to subscribe to that team's topic. Pretty much, it's a little bit more complicated than this, but pretty much the first consumer that shows up, it says, hey, you're the group leader now. And then when other consumers show up, it says, your group leader's over there. And then the workers kind of work amongst themselves to assign partitions of the topic to each worker. The server knows pretty much nothing about that. I also bolded the word partitioned here, so I want to talk a little bit about that. In Kafka, topics are partitioned, and messages in a single partition are guaranteed to be read out in the order that they're inserted. But messages in separate partitions have no relative ordering to the messages in the other partitions. So if I put 1,000 messages in partition 1, and then 10 minutes later put a single message in partition 2, the message in partition 2 could be consumed before most of the other messages, depending on how fast your consumers are working. So why do people go to event streaming platforms? And there's a lot of use cases for this, and I'm going to leave out a bunch of them. I'm not talking about big data, analytics, data warehousing, those kind of use cases. I'm talking about it from the point of view of backend application developers, which I think a lot of us probably are. And I think people are trying to avoid this, which I call microservice madness. When you're doing like microservice RPCs to each other, you end up, every time you add a service, you potentially increase the number of connections between services exponentially. And the thought, at least when I started initially reading about this many years ago, was that streaming was a solution for this. You take all those conjoined boxes, you put them vertically, and now each application publishes their own data, so they have like one outgoing stream, and then whatever data they care about coming in, they read off the message bus or Kafka or whatever. And I think there's a hypothetical ideal here, and that is that teams work on their microservice, they publish all of their data, and other teams somewhere else in the company can ingest that data, do whatever they want with it, and they can do it kind of autonomously and decoupled. It's streaming, so it's low latency. The data, like if they've ingested it to their local database, you can get low latency because now you can just do joins in your database against some other team's data. You don't have to RPC over the network. And this sounds great. It sounds really simple. But could it be a trap? And yes, it is a trap. There's a ton of hidden coupling here that you don't see. For example, if that red application box was player stats or something, and it deals with like baseball player stats, and it has a player name field in all their messages, and then they realize, oh, we actually need first name and last name because we need to, I don't know, group the players by last name to figure out who's related or something. If they change that and they drop the player name field and add first name and last name, then all their downstream consumers can break because they didn't know about that change, right? You still have that same problem you had with RPCs before. Now, all your other applications also need to have an ingestion process. How do they get the data from Kafka? How do they pull it into their database? Where do they store it? How do they index it? How do they retrieve it? And there's perhaps an even worse second level of coupling that you don't think about. Now all your consumers have a hard dependency on how much data you publish, if they're ingesting it all, right? So if the player stats service no longer just does baseball, it does baseball, football, tennis, and flip cup or something, you now publish 100 times the data, and now all your downstream consumers have to be ready for that. Maybe their database isn't scaled big enough because they're ingesting all your data. Maybe their indexes are bad. So I would say, am I saying it's a trap? Well, I think there's trade-offs. There are different trade-offs, right? And there's things you have to think about, and I don't think they're generally explained up front. So given that, I want to talk about how we've kind of dealt with this at theScore and how it's helped us scale our teams and our software. On the team front, I mentioned before we went from 8 teams to about 25 teams in 2 years. We split our teams into core teams that work on the core backend services and feature teams that build features on top of that. And for me, scaling teams is all about decoupling teams, providing them with autonomy, and simplifying the communication paths between them. And that's like you can't solve those problems. They exist no matter what. But there's some tools that we use to help with that. Kafka, that's why we're all here today. Protocol buffers, and then on top of Kafka, we have protocol buffers, schema registry, some linters, and an internal service called DataDex. I'll break all these things down here. So on the message encoding and tools, protobuf, if you're not familiar with it, it's an encoding format. Interesting fact, like parts about it are that the schema are stored separate from the message payloads, and you need the schema to decode the messages. But the nice part is you can use an older version of the schema to decode your messages. So if I update my schema, I add some fields, some service that doesn't know about that new schema can still pull the data out of those old messages. And then schema registry, it's a Confluent product, builds on top of that. And it allows me, when I publish a message, to also publish the schema to the schema registry, and then some consumer downstream, when they get the message, they can say, there's a new schema for this, let me go fetch it, and then it has the whole new schema. It also has some options where you can say, don't let someone publish a schema unless it's backwards compatible. So we can kind of stop that problem of like, I changed my player name to first name and last name. When you go to publish that schema, the schema registry is like, nope, sorry, that's a breaking change. I'm not going to take it. And you can turn that off or whatever, but it's a nice feature. To take that a step further, we use some linters. There's a really good one called buff. We commit all of our protobufs to a shared repository. And this shifts left that process of blocking those changes a little bit. As soon as you commit your schema change to the repository, the linters run and say, you're changing this field. I think it even goes as far as detecting changes in the generated source code from the protobufs. But the point being is that when you're initially making that change, it says, hey, whoa, you can't do that. You're going to break this for people. It makes you have that discussion of like, well, what teams are using that field? Do I need to go talk to them? I'm going to add a first name field and a last name field, have them update, and then maybe eventually we can depreciate that field. But it moves that discussion up front rather than in the RPC world. You could just publish your service, your schema's changed, but there's no real schemas if you're using like JSON or something. You break some services downstream. Hopefully it gets caught in QA, but maybe it makes it to production, right? So this forces all those conversations to happen up front, which I think reduces a ton of friction in the development process and helps teams communicate a little bit easier. The other thing I wanted to talk about in this category is a service that we have internally called DataDex. It's a self-serve materialization. I've given a couple talks publicly about DataDex before, so if you're interested in it, check those out. There's absolutely not enough time today to talk about it in depth, but I do want to kind of cover what it does. So I said self-serve materialization of Kafka topics. It kind of has a sidecar model, and the way it works is teams stand up in their data center, in their namespace, Kubernetes namespace, right next to their service. They stand up an instance of DataDex. And all it takes from a team is they define the data that they need from Kafka. So they can say, ingest the sports scores topic. And then they define the indexes they need over that data. I need to index by team. And then it gives them really fast, low latency queries for that data. And this solves the problem of teams having to have like their bespoke ingestion process on like, how are we going to get the data from Kafka? How do we store it in our database? How are we going to index it? We've kind of abstracted that away at a platform level. It also has this cool bonus watch feature where we can connect from like edge services. We can connect Absinthe GraphQL subscriptions to DataDex and have it watch the Kafka topic and push messages out to the services and then streamed out to our clients. It's pretty cool. I talk about that in some of the other talks on the topic. But that's kind of solved that problem across all of our teams. So that was how we use it to scale teams. Let's talk about the software itself. Kafka is really fast, and that helps a lot in scaling. The Confluent basic size instances can ingest about 250 megabytes a second. I'm just using Confluent as an example here because I could easily pull these numbers off their website. If your message payload size is about 2K messages, that's 125,000, or 2 kilobytes per message. It's about 125,000 messages a second, which is, it's okay. If you pay more and use their dedicated cluster, you get about 50 megabytes a second per Confluent Kafka unit. You can have up to 24 Confluent Kafka units, which gives you about 600,000 messages a second. Like, that's pretty good. And apparently, if you ask really nicely, they can give you 100 CKUs, which will get you 2.5 million messages a second. And that's at a 2K payload. If your payload's smaller, you get even more. But you'll notice all these numbers are in megabytes a second, not like messages per second, because all Kafka really cares about is that it's delivering you the bytes that are in that log. It doesn't really, doesn't split up messages and send individual messages to consumers or anything like that, like some other messaging platforms do. And you can also run multiple clusters if you need more than 2.5 million messages a second. In addition to just speed, we get some resiliency and durability aspects out of it. The topics are replicated between brokers, so if a broker fails, we have a backup data. It helps scale your workers horizontally through partitioning. That's a blessing and a curse because whatever the number of partitions you have, that kind of caps your max concurrency for workers. So if you set it to, say, 6, you can only ever have 6 workers. You can repartition topics, but if you have historical data in those topics, it's not an easy task, believe me. So you probably want to pick a larger number. For me, a good place to start is like 32 or 64. It really depends on the work that you're doing. But if you check with your Kafka vendor on how many partitions they support, it's usually in like the thousands. It depends on the size of the instance. So you can have a lot of partitions. We also use it to enable change data capture. Datadex kind of plays into that. But we're able to have all of our services publish the events that happen inside them, and then other teams can watch them for changes, ingest their data into Datadex in our case. But I think it's really important when you're talking about dealing with backend applications that you don't publish your whole table to Kafka, that rather you model like domain events that make sense to the other teams. You don't want to publish your whole database schema, which you can do. And I like to say it like this: friends don't let friends Debezium their tables. There's a Java application, I guess it's a Kafka Connect connector called Debezium. You can just say, like, look at this Postgres instance and take these tables, and every single change that comes into that table, put it into Kafka. And there's some use cases for that. I think it's used a lot in like big data where you want to ingest application databases into like a data lake or something. It's very useful, but I think if you're talking about backend teams working together, that's not the best solution because then your downstream consumers are coupled to your database schema, right? If you ever need to denormalize your schema or change it for any reason, like you've just broken all your downstream consumers. So you should be modeling them as like domain events rather than just whatever your table happens to be. Okay, this is an Elixir conference. Let's talk about Kafka on the Beam. Roll up your sleeves. Going back to this book, this was a Java book, and it started, like looking at it in hindsight, this sentence about it being a distributed event streaming platform makes a lot more sense now. The word platform here implies that it's not just that server that sends you bytes off of a topic, it's the whole ecosystem around it. There's tons of libraries in there's the main libraries, but then there's a lot of stuff built around it, like Kafka Streams, there's Kafka Connect adapters, there's KSQL, and all of that is kind of in the Java ecosystem. Some of them you can use outside of Java, like I think you can use KSQL, no problem, but you have to then run it. And if you don't have expertise running Java applications at scale in production, it can be a bit challenging. But on the Beam, we have a couple good libraries. We have Broad, which is what we use, and there's also ElixirConf, which is kind of newer and binds to the C Libardi Kafka. But those libraries, they're the basic Kafka libraries, right? They read the data off the topics, they can do consumer groups, but that's kind of where it ends. And there's some problems it doesn't solve. The first one being that messages off Kafka must be processed sequentially. And this is, I don't know about you, this is how I visualize like message queues and buses and stuff in my head. You get like little tubes, and the messages can be like little blocks that float through. But here, there's something kind of weird with this message, and then it gets worse, and it's blocking the whole tube. Now no more messages can be processed. We're stuck, and this is called a poison pill. You have to address this somehow. You either need to have like somebody come in and fix the code, or do something else. And the reasons this can happen is like maybe you can't deserialize the message or something, or maybe for you to process it, you need some other data that should be in your database but isn't. And because in Elixir, we let things crash, so you get an exception when you try to process this thing. Your consumer crashes, it restarts, you read it again, you try to process it, it crashes, restarts. That's not great. So what can we do about that? We can take the message and move it somewhere else. It's called the dead letter queue. And this isn't like particularly unique, but Kafka has no concept of a dead letter queue. Other messaging platforms like RabbitMQ do. They have specific dead letter exchanges, and RabbitMQ can move your message from your normal exchange to a dead letter exchange after a negative acknowledgement or a timeout, and that can even go as far as like trying to redeliver those later after a delay. Kafka Streams on the Java side, it doesn't do dead letter queues, but it has a lot of primitives that make it really easy to set that up with a couple lines of code. On the Beam, it's kind of DIY. For us at theScore, we tend to save our poison pills in the database of the consuming application, because there's really no point to like publish it back to a Kafka topic if that's the only application that'll ever look at it. But it's not that hard either, but it's something you have to address when you're running production systems with Kafka. The next thing we need to address is a common distributed systems problem. It's called the two kernels problem. The guy on the right here, the kernel here, says, dinner at 4, circle yes or no. He wants to go down there and get that chicken and maybe make some fried chicken. So he sends it across this valley to the other kernel. But at this point, he doesn't know, did he not get my message? Or did he get my message and hasn't replied? Or maybe he sent the reply and I just didn't get it. He doesn't know. The guy on the other side, he got the message. So he circles yes and sends it back. At this point, he doesn't know if the other guy got his message. And if he shows up at 4, did the other guy get his acknowledgement, or is he not going to show up? And there's no way, like impossible, given time and space, for both these guys to agree when to show up to fry up this chicken. And it can't be solved, but it can be worked around with transactional producers. And this is the two generals problem, not the two kernels problem. Anyway. The way we work around this is when we're making the changes to our database that we're about to publish to Kafka. So that guy, the change was he got some chicken. I must have been really hungry when I was making these slides. At the same time that you make your change, you also, in another table, insert an intent to publish a message. It can be the message itself or some other kind of identifier. And in the same transaction as the change you're making, you commit that to the outbox table. So now you have an atomic record of, I made this change, I need to publish a message about it. At that point in time, you have a set of workers, or after that, I guess, you have a set of workers that kind of rolls through, picks the messages up out of the outbox, and delivers them to our topic. I think oftentimes OBAN's used like this, right? Like you make a change, and then in your transaction, you insert your OBAN job. And then the Java way to do this is you would probably write the whole message to your outbox and then use Debezium, and it actually can pull the message field out of the table rather than publish the whole table. You could do that in Elixir too, but it's just as easy to kind of do it ad hoc. Okay, so those are the two things you need. You need the transactional outbox and you need dead letter queues. And then there's some nice to haves, and they mostly deal with performance. Producer concurrency. So we talked with that transactional producer. It's really important that every message is produced in the order that it was created as you're putting them in the outbox. So the simple way to do that is you have one producer roll through that outbox and produce all the messages in order, because they need to get into Kafka in the order that they happened in your database. So Kafka, well, what it does, it partitions the topic by taking your key and hashing it over the number of partitions that you have. We can take that one step further in our database for our outbox, and rather than hashing over the number of partitions we have, we can hash over like the whole integer key space. But the important thing is that whatever your key is for your message, it might be like a user ID or something, whatever your key is, all the messages for that key end up in the same partition. So our outbox might look like this. We have our IDs, we have the key hash, and then we have the messages, which don't really matter for our sake. But the outbox partitions go from just having a few, like you have Kafka partitions, to being able to have millions, right? And then what we have, in addition to the outbox table, we have what we call a slices table. And that just, each row represents a key, like a range over the possible keys in the outbox. So the first row here starts with 0, goes to 4,000, the next one 4,001 to 8,000, et cetera, et cetera. And then when you need to produce the messages that are in the outbox, one of the producer processes, and now you can have many, grabs one of those rows out of the slices table with a Postgres select for update skipped locked statement. And what that does is if there's other producers that have already grabbed a row, they just don't see them anymore. So the next producer that comes along will grab the next row. And this guarantees that, so you have your key range, right? Like my producer will now work on 0 through 4,000, goes back to the outbox, selects messages from the outbox ordered by the primary key, where the hash is between 0 and 4,000. So I've claimed that chunk, and then I produce those messages in the order that they were inserted into our database. And so one thing that changes here is Kafka guaranteed all the messages within a partition are ordered. This kind of loosens that up, and now all the messages for a given key are ordered. And that gains us a little bit because we don't really care about the relation between my records and Frank's records. We just care that all my records are ordered. There's a little bit of bonus content here. You could also do this with database triggers to simplify the process so teams don't have to add this outbox thing into all their applications. But you need to use the same hashing algorithm that you would use on the Elixir side. We use UMurmur2, which I think is like the default Java hashing algorithm for Kafka. But it doesn't exist in Postgres, so we can write it in Postgres. And I did. And you probably can't read that code, and you don't want to, and I don't ever want to read it again. I don't really trust my PostgreSQL to like that extent. So I was able to use property tests in Elixir, where I could take the implementation we had in Elixir as like my model in the property test, generate thousands, millions of strings, and run them through the Elixir version and run them through you run it through Ecto into Postgres to do the same hashing on the Postgres side, and then compare the results. And I actually found a couple bugs. I think they were around like null characters and stuff, but the property test saved me from potentially some bad times. Now that our producers are concurrent and fast, we want consumer concurrency. So we want to split. So Kafka gives you a batch. It gives you a batch of bytes, and then the client libraries parse it out into individual messages. But you'll be delivered tens, hundreds, thousands of messages depending on the message size and whatnot. But again, if we can partition them by the key rather than just the partition that they're in, and we loosen that same guarantee of per partition ordering to per key ordering. And Elixir makes it super easy because of our concurrency primitives. So we have our process message function. We partition our message. We group them by the key. We use task supervisor async stream to create a bunch of tasks. In each task, so we have a task per key. In each task, we have to process those messages sequentially, though. That's what the for block does. And then we take that stream of tasks, put it in another task, and run the stream. And then we yield that kind of parent task with a batch timeout. And batch timeouts, this is kind of a little word of warning. If you don't, there's timeouts that you set up in Kafka and on your clients, and if you don't consume a batch fast enough, it thinks your consumer's dead, and it kicks you out of the consumer group. And when that happens, we talked about the consumer groups all coordinate over that hidden topic. Well, all the other consumers need to consume the message that you got kicked out, and if you're doing a bunch of work and they don't get that message, they'll also get kicked out. So you run into this problem where if you consume too slowly, you basically boot all your consumers out of your consumer group, and that's not a good time. So point being, timeouts on your batches are really important. So Kafka on the beam. It's not batteries included. Things you need to consider, kind of recap, are the dead letter queues, transactional producers, producer concurrency, consumer concurrency, and materialization's cool. If you're going to do this in production, I think you need the dead letter queues and the transactional producers. The other things are kind of nice to have. So overall conclusion is you might not even need Kafka, right? If you're a small team, you don't plan on a lot of growth, you're not dealing with millions of messages a second, something else like RabbitMQ might be more suited for you, plus it runs in Erlang, so if you're familiar with running things on the beam, like it's maybe not a bad match. The Elixir ecosystem is kind of lacking in some areas, so be prepared to do some DIY. I don't know about you. For me, I love doing that kind of DIY work, but you might not want to take it on right now. Given all that, I think it's still worth it, depending on your team size, your goals. There's a lot of it depends there. With that, that's the end of my talk.